I don't have any problem to share, but the problem is that if I shared it, then nobody will watch my video on YouTube. I need more subscriber and watch time also. Some people said to me, start some paid service, but till now I did not start any paid service. I need only your love and support. Please like and subscribe my channel as much as you can. That will be the great motivation for me to continue my YouTube services with you. I am providing these services totally free of cost. Let's start with TFET. TFET. TFET is tunneling field effect transistor. Have been one of the major device candidate for reducing the supply voltage and power consumption. Since they can overcome the thermonic emission of Sath-Shu's law, the low on current issue of TFETs has been shown to have several solutions such as there is a one drawback of the TFET, it has low on current. The low on current of the TFET can be improved by using different technique. The first technique is using 3,5 compound. For study how 3,5 compound increase the on current, please follow these paper that can help you to explain how 3,5 compound increase the on current of TFET. One more solution is 2D material. Please follow these paper to understand how 2D material helps in increasing the on current of TFET. The first paper is 2D tunneling field effect transistor using WSE2 SNSE2 hetero structures. The second paper is Saming Murera down to 1 nanometer channel and anisotropic effective mass. These are 6 to 7 paper to explain how the 2D material increase the on current of TFET. The next solution is vertical TFET. Vertical tunnel field effect transistor based on band-to-band tunneling mechanism. Although a prototype vertical tunnel field effect transistor has been experimentally fabricated and shown to have a steep subthreshold slope, but it still suffers from the low on current. By using different techniques such as stained silicon, 2D material, we can improve the current level of tunnel field effect transistor. 2D materials can serve as ideal channel material for vertical field effect transistor. Vertical tunnel field effect transistor due to their excellent device characteristics, lack of dangling bonds at interface and the variety choice of material selection in 2D section. As MOSFET are scaled down below the 45 nanometer, the problem arise such as show channel effects and the eye of leakage current grow drastically because of the conduction mechanism of the MOSFET, that is thermonic emission, and the subthreshold slope is restricted to 60 millivolt per decade. As tunnel field effect transistor step down the subthreshold slope to less than 60 millivolt per decade by utilizing quantum mechanical band-to-band tunneling mechanism, due to which the performance of the circuit for low power application improved. Further, with gate work function engineering, the tunnel field effect transistor can be tuned to achieve a higher on current as well as low off current. In the proposed structure, I will do the gate engineering by introducing 3 metal gate to improve the on current. Vertical structure of tunnel field effect transistor is not bounded with the constrained channel length and widen their scalability down to 10 nanometer. This means in case of vertical TFET, we can scale down the channel length up to 10 nanometer. There are two type of TFET structure here. First one is the lateral structure, that is the lateral TFET, or we can say that horizontal structure. And the second one is vertical TFET, vertical structure. Later TFET is a PIN structure with gate over the intrinsic layer. In this structure, tunneling is take place at the source channel junction. You can see that in the figure. It is a horizontal structure. If you want to scale down the gate length, you does not scale the current. Horizontal TFET has a simple design and it can be implemented in vertical nanowire. The disadvantage of this structure is the tunneling is only occur at the gate edges. And the second one, gate alignment and source profile is very critical in case of horizontal TFET. If you scale down the gate length, then there is a direct tunneling at the source to drain region take place. This will increase the show channel effect in the device. Second one is vertical TFET, vertical tunnel field effect transistor. You can see in the figure. Vertical TFET is a different type of structure. In such a structure, you have seen that a P plus layer undercut from the drain. Undercut is very important. If P plus layer continues up to the drain, then there is a direct source to drain tunneling take place. This will increase the show channel in the device. Due to undercut, the gate has more control on the channel. The advantage of undercut is that it will enhance the gate control on the tunneling area. Now the gate has more electrostatic control on the channel. This will eliminate direct source to drain tunneling. But there is some few advantages of the vertical TFET. The disadvantage of vertical TFET is due to the reduction in the gate length, which is directly proportional to the current. If you scale down the gate length, then the current is also decreased. One of the major drawbacks is that it is difficult to fabricate as compared to later TFET. One more thing you can observe in the below these figures. If the two quantum valve p-type and n-type is placed horizontally, then the drain current is directly proportional to the BOL की power 3 by 2. But if the tunneling is across the area of the quantum valve, then the on current will increase stepwise. This will reduce the subthreshold slope to a minimum level and increase the switching speed of the device. There is a two variation of vertical TFET, like first one is the air bridge structure and the second one is the pillar structure. The structure is almost the same like, but there is some sort of difference in the fabrication process. You can see that both the structure in the off state as well as on state. When both the structure is in off state, gate to source voltage is 0 and the VDS voltage is equal to the supply voltage. I have drawn the parasitic path. This one, parasitic tunneling path. This parasitic tunneling path can limit the off current and degrade the switching performance of vertical TFET. This means we have to eliminate this parasitic tunneling path. Next is the impact of parasitic tunneling path in the vertical TFET, in which I have shown the four tunneling paths A, B, C and D. From this figure, drain current versus the gate voltage, you can notice that the A path is first one to turn on, but it has the longest tunneling distance, so that it has low on current. After that B on, after that C on. ABC tunneling path is due to the parasitic diagonal tunneling. And finally in the last, D is the desired tunneling is turned on. The disadvantage of A to C tunneling path significantly reduce the sharpness of the on current. This means in the simple language we can say that it will increase the subthreshold slope. Next is the one of the type of vertical TFET, that is electrostatically doped vertical bilayer TFET. In bilayer TFET, we don't put any doping in the channel region. In top gate, giving a positive voltage and the bottom gate connected to the negative voltage. The bottom gate dielectric has thicker dielectric. Later electric field can be greatly reduced using thicker bottom side oxide layer, and it will also reduce the parasitic diagonal tunneling in the vertical TFET. Advantages of this device: no doping in the channel region, top gate accumulate electrons and the bottom gate accumulate hole. Carrier inherently align with the gates. One of the other advantages is it will eliminate problem caused by the doping, band tails, dopant diffusion and the implant damage. And the last one is the most important, it will eliminate parasitic path tunneling. This will help in to reduce the substrate slope to a minimum value. The vertical TFET is an attractive structure but faces difficulties with the electrostatic control of the channel. A diagonal parasitic turning path can severely diminish both off current and the on current of the device. Different type of structure must be designed to prevent the parasitic turning path. One of the example is electrostatically doped vertical bilayer TFET. This is my proposed structure of vertical TFET. For all the three regions, source, drain and channel, silicon material is used. While HFO2 is used as a oxide layer, the metal gate is divided into three electrodes, Mg1, Mg2 and Mg3. Mg1 is the metal electrode at the drain side, Mg2 is the middle gate electrode, Mg3 is the metal gate electrode at the source side respectively. Lg1, Lg2, Lg3 are the length of the metal gate Mg1, Mg2 and Mg3 respectively. The work function WEF1, WEF2 and the WEF3 is the gate work function of Mg1, Mg2 and Mg3 respectively. Heavy doping is used for source and drain region while channel region is moderately doped. Next is the variable of the proposed device. Source doping concentration 5E20 per centimeter cube, channel doping 1E16 per centimeter cube, drain doping concentration 1E20 per centimeter cube. Metal gate length Lg1 15 nanometer, metal gate length Lg2 20 nanometer, metal gate length Lg3 is 50 nanometer and the channel length is 50 nanometer. Metal gate work function 4.15 electron volt for WEF1, for WEF2 4.30 electron volt and for WEF3 4.15 electron volt and the gate dielectric thickness is 1 nanometer. Let's go to the most important part of this video is the code of vertical TFET. Again, the code started with the statement go atlas. Defining mesh for the device. Meshes should be as fine as possible, meeting the computer resource constraint. Mesh space.mult is 1. This means this meshing is multiplied by a factor 1. Meshing start from the location 0 up to the 50 nanometer. At first location 0, the spacing is 0.025. Second location 2 nanometer and the spacing is 0.001 nanometer. Please note out this meshing very carefully. I have made the required changes in the meshing to optimize the device. By meshing, it starts from the 0 and it is end at 150 nanometer. For 0 to 5 nanometer, the spacing is same 0.001. At 30 nanometer, the meshing is make more fine 0.8 nanometer and up to 80 nanometer. The meshing is same 0.8 nanometer and after that up to 150 nanometer, the meshing is approximate 1 nanometer. Next is defining region and material of the device. Region number 1 from Y minimum to Y maximum up to 150 nanometer and the X minimum to X maximum up to 50 nanometer. The material is oxide layer SiO2. Region number 2 for minimum value of Y to the maximum value 30 nanometer and in the X direction from 20 nanometer to 30 nanometer. The material is silicon. For the region 2, 3, 4 and 5, the material is same, that is silicon. You can note down their positional parameter. And the region number 6 and 7 is for hafnium oxide with their positional parameter. Please note down everything very carefully. Next is defining electrode. In the proposed structure, the metal gate is divided into three electrodes: gate 1, gate 2 and gate 3. The first electrode is drain with their positional manometer. Second electrode is gate. Third electrode is gate 1 and the fourth electrode is gate 2. We are using the three gate, gate 1 and gate 2 with their positional parameter for one side, and the other side again gate 1 and gate 2. Next one is the source electrode. Next is the source 1 electrode, and the last one is source 2 electrode with their positional parameter. The doping, next is the doping. The doping profile is assumed to be abrupt. We are using the substrate has the higher doping 5E20, and the source also has the higher doping 5E20. Drain has low doping 1E17, and the channel has doping 1E16. Next one is the quantum mesh. Quantum mesh location start from the 50 nanometer in the x direction up to 35 nanometer. Initially the spacing is 0.0001 up to 3 location: 15 nanometer, 21 nanometer, 29 nanometer, and the last one for 35 nanometer the spacing is 0.001. Please note down the quantum tunneling meshing in y direction with the location 25 nanometer up to 150 nanometer. I have changed the quantum tunneling meshing in y direction. Please note down carefully from 25 nanometer to 150 nanometer. Initially the spacing is 0.0001, after that 0.001, after that 0.0001, and the last one is 0.001. Next, defining contact. Gate WEF1 work function is 4.15 electron volt. WEF2 gate work function is 4.3 electron volt, and the WEF2 gate work function is 4.15 electron volt. Common gate means we are applying the same voltage to all the gate material. Next one is the contact name source. Next is source 1, next is source 2 in the common source. Next, save the function. You can observe the output in the Tony plot. Next is the model: concentration, mobility, BGN, SRI, CVT, Fermi. You can note down. Solve initial. Next is the method: Newton trap. Next, biasing to the different region: source, drain and gate, starting from 0. In order to improve convergence, drain voltage is increased gradually from 0.03125 volt to 1 volt. Next, log file and save with the name TFET1. Solve AC frequency to find out the conductance and capacitance from we get 0 volt to 1 volt with the stepping 0.1 volt. Next, save the log file and you can see the log file in the Tony plot. After that, we are using this command output balance band conduction band to find out the various parameter in the structure file. One is, and the last one is save the structure file, and you can observe, you can see the structure file in the Tony plot, and the last one is quit. When you run this program, you will find two files. One is the structure file and another is log file. This one is the structure file. The metal gate is divided into three metal with different material, and the another one is the log file. The off current is approximate 10 raised to power minus 17, and the on current is approximate 10 raised to power minus 4 with an optimized sub-threshold law. If you want to extract the data, click on file option, export, select CSV. Data will save into Silvaco code and VTFET folder with the name export1. Next is the variation in work function at the source side. Figure show the ID VGS curve for WEF3 varying between 4.1 electron volt to 4.8 electron volt with WEF1 and WEF2 fixed at 4.15 and 4.30 electron volt respectively. The variation in on current takes place by changing the work function near to the source channel interface, and there is almost no change in the ambipolar current by changing the value of work function WEF3, that is near to the source channel interface. Next is the variation in work function at the channel. Figure show the ID VGS curve for WEF2 varying between 3.9 electron volt to 4.6 electron volt. There is a small change in the ambipolar current, and the on current take place by changing the middle gate work function. Next is the variation in work function at the drain side. Figure show the ID VGS curve for WEF1 varying between 4.1 to 4.5 electron volt. With increase in WEF1, the length of the tunnel path reduces at the drain channel interface, so that it will increase the ambipolar current in the device. As you seen in the figure, as we increase the work function at the drain channel interface, there will be no change in the on current, but there is some change in the ambipolar current. The ambipolar current start increasing as you increase the work function from 4.1 to 4.5 electron volt. And last one is the oxide thickness variation. Figure show the variation in ID versus VGS curve with change in the oxide thickness. With decrease in the oxide thickness, the net effective electric field present at the gate region is enhanced, which result in downside band bending of energy band at the source channel and drain channel interface. This downside band bending is responsible for increase in the on current as well as ambipolar current. Now the improved current is observed in the figure, on current as well as ambipolar current. My dear students, if you are searching a new domain area of your thesis work, then vertical TFET is one of the best options. You can design electrostatically doped vertical bilayer TFET, which has lots of advantages. The main advantage is it will eliminate the parasitic tunneling path, which result in poor subthreshold slope in vertical TFET. There are lots of vertical TFET structures in which researchers are working and giving their best. You can use also 2D material as a base material, but you cannot implement 2D material appropriately in Silvaco Atlas TCAD tool. For simulating 2D material, you have to use QTK software. My dear friend, this is all for today. Please